Challenge. So let us start. Bismillahirrahmanirrahim. In today's lecture, I want to demonstrate a few examples, a few numerical examples for the BJT transistor. We have done a variety of configurations for the BJT. These configurations include the common base configuration, the common emitter configuration, and the common collector configuration. And in today's lecture, I want to demonstrate a few numerical examples that will cover the above mentioned configurations. So let us come to our first example. This example is in the case for common base configuration. And the question statement is, for the common base circuit shown in figure below, determine IC and determine VCB. Assume the transistor to be of silicon. So what we have to find in this numerical example is that we have to find the collector current and we have to find the voltage collector base. So let us look at the diagram. In the diagram we see, first of all, VEE. It is the external power supply of 8 volts connected between the base and the emitter. This is the base terminal and this is the emitter terminal, and here is the collector terminal. So we have to find the collector current and we have to find the voltage between VCB. This is V, C and B. The given values include voltage EE, it is equal to 8 volts. Then we have the base and emitter junction. It is of silicon, therefore this voltage will be 0.7 volt. It is understood this is 0.7 volt because of the PN junction. Then in series with the emitter is a resistance called RE, and its value is equal to 1.5 kilo ohms. Then if we look at the collector side, we have an external voltage source VCC equal to 18 volts and a series resistance, RC, which is in series with the collector, and its value is 1.2 kilo ohms. We have to determine the collector current and voltage collector base. So let us start with the solution. The solution is, the first is that since the transistor is of silicon, therefore VBE is equal to 0.7 volts. The voltage between emitter and base is equal to 0.7 volts. Right, next, let us look at the circuit. Let us find emitter current. Let us try to find emitter current. From VEE, there will be a current called the base current. It will flow from the base to the emitter and then into RE. This is called the base current. And through RE, we will have an additional current flowing from the collector into the emitter and into the resistance RE. This is the IC, such that I emitter is equal to the collector current plus the base current. So the total current that flows through RE is equal to the emitter current, which is the sum of collector current and the base current. Now let us apply Kirchhoff's voltage law to our emitter circuit. The emitter circuit has VEE as the voltage rise and voltage base emitter as voltage drop and voltage VRE as the voltage drop also. So by writing the Kirchhoff voltage law, we get VEE is equal to IERE plus VBE. ये सबको समझ आ गया? ये VEE is equal to IERE plus VBE कैसे आया है? ये हमने Kirchhoff voltage law लगाया to the emitter side. So by rearranging, we get IE is equal to VEE minus VBE over RE, and these values are given. VEE is equal to 8 volt, VBE is equal to 0.7 volt, and RE is equal to 1.5 kilo ohms. So emitter current is equal to 4.87 milliampere. Emitter current is equal to 4.87 milliampere. Now at the end, it has written that IC is approximately equal to IE is equal to 4.87 milliampere. Why is IC approximately equal to IE? Why is collector current approximately equal to emitter current? The reason is that the relationship between collector current and emitter current is equal to IC is equal to alpha into IE, where alpha is normally equal to 1, very close equal to 1, very closely equal to 1. Alpha is normally equal to 1. Therefore, IC is equal to IE, or collector current is equal to emitter current. Now, we have found collector current. The next undetermined value is voltage between collector and the base. We have to find voltage between collector and base. This is the collector and this is the base. We have to find voltage, collector and base. And we can find voltage, collector and base if we apply Kirchhoff voltage law to the collector side. That is, if we apply formula VCC is equal to IC into RC plus VCB. So we look at this loop. Here VCC is the voltage rise. Voltage across RC is called VRC, and it is equal to the collector current multiplied by RC, and VCB is the collector base voltage, and VCC is equal to ICRC plus VCB. We can rearrange this equation for VCB and we find that VCB is equal to 12.16 volts. So this is our second part of the solution. So this was the example 1. Now we come to the second example. The second example is again for common base configuration. The statement of the example is: the transistor shown in figure 4.11 has the characteristic curves shown in figure 4.10. When VCC is set to 25 volt, it is found that collector current is 8.94 milliampere. Then find the alpha of the transistor and repeat if collector current is equal to 1.987 milliampere when VCC is replaced by a short circuit to ground. So in example 4.2, we have the circuit shown in figure 4.11. Let us first look at the figure 4.11. Here is the base terminal. Then this is the emitter terminal. And this is the collector terminal. We have to find alpha. Alpha is to be found. Alpha is the relationship between collector current and the emitter current. Here is the collector current, and from the emitter we will have the emitter current. This is the emitter current. Whereas alpha represents the relationship between collector current and emitter current. And then between the collector and the base is a variable power supply called VCC. It is variable because of this arrow. And between emitter and the base there is a power supply of 0.7 volts. This 0.7 volt battery or power supply source is external. We have to find, in the first case, we have to find the value of alpha. We can neglect ICBO. And in the second case, we have to find if collector current is equal to 1.987 milliampere when VCC is replaced by short circuit. So let us come to the first part of the solution. Let us solve for the first part. And to solve the first part, a graph of characteristic has been provided in figure 4.10. This figure 4.10 displays common base input characteristics for NPN case. On this graph, there is voltage base emitter on the x-axis and emitter current on the y-axis. We can see that on this characteristic, voltage base emitter exists on the x-axis, whereas emitter current exists on the y-axis. Then we have a number of graphs. Each graph is between VBE and emitter current, but for various values of collector base voltage. The first graph is for VCB equal to 10 volts, equal to 0 volt. The second graph is for VCB equal to 10 volts, and the third graph is for VCB equal to 25 volts. Since in part number 1, the applied voltage VCC is 25 volt. Now, how am I saying it is 25 volt? It is given in the problem statement that VCC is equal to 25 volts. And in the circuit, we can see that VCC is directly connected between collector and base. So VCB is also equal to 25 volts. Because there is no resistance given in the circuit, all VCC is appearing across collector base terminal, and therefore VCB voltage collector base is equal to 25 volt. Now in out of these three graphs, we have one graph which is valid for VCB equal to 25 volt over here. So we will follow this graph such that this graph shows or tells us that when we have VCB equal to 25 volt, then for what value of base emitter voltage, what will be the value of emitter current? So we will follow this third line, this third graph, and voltage between emitter and the base is 0.7. This is on the graph, this is 0.7. So on this graph we have 0.7 and it corresponds over here, or it intersects our characteristic at here, and this corresponds to IE equal to 9 milliampere. So in figure 4.11 we see that VBE is equal to 0.7 volts. From figure 4.10, the vertical line corresponding to VBE equal to 0.7 volt intersects VCB at 25 volt at 9 milliampere. Therefore IE is 9 milliampere and IC is already given equal to IC is already given equal to 8.94 milliampere. Therefore, alpha for part number 1, alpha is equal to collector current divided by emitter current is equal to, collector current is 8.94 milliampere and emitter current is 9 milliampere, and the ratio is equal to 0.993. It is unitless, almost equal to 1. So this was the solution for part number 1. Now we come to the solution for part number 2. In part number 2, it is written, repeat if now collector current is 1.987 milliampere when VCC is replaced by a ground. So in other words, now VCC is short circuit, there is no power supply, voltage between collector and the base VCB is now equal to 0 volts. 0 volt. VCB is equal to 0 volt. So to solve for part number 2, we look at the common base input characteristic and look at the graph which corresponds to collector base equal to 0 volt. It is over here. This is the graph which corresponds to VCB is equal to 0 volt. And the voltage between emitter and the base is still 0.7 volt. So this is 0.7 volt. And we have to see that the vertical line corresponding to VBE equal to 0.7 volt intersects this 0 VCB. It is IE emitter current equal to 2 milliampere. Therefore, alpha, which is equal to collector current divided by emitter current, is equal to 1.987 milliampere divided by 2 milliampere is equal to 0.9935. This was the solution for part number 2. Now let us come to the third example. The third example is for the configuration common emitter.
Sir,
G.
sir, how we came to know that The curve with VCE is equal to 25 volt is ideal curve.
Can you please repeat your question?
Sir, I'm saying that how we came to know that the curve with the VCB voltage is equal to 10 volt is an ideal curve. Why didn't we take VCB is equal to 0 or 10 volt? Why we take 25 volt?
Because in the first case, in the first part, the statement says that VCC is 25 volts. Do you see this over here? VCC 25 volts.
Yes,
And
sir.
if you look at the diagram, VCC is directly connected across collector and the base. There is no resistance in this circuit. Now, figure 4.10, the characteristic graph of figure 4.10 shows a variety of graphs, 3 graphs for various values of VCB. We have to select that graph which corresponds to collector base voltage of 25 volt, because in our case VCB is equal to 25 volts. So to meet this requirement, our third graph, which is drawn for VCB is equal to 25 volt, we will follow or we will adopt this graph for part number 1. And further onwards, we see that we look or we observe that when voltage base emitter is 0.7 volt. Why is 0.7 volt? Why is 0.7 volt very important? Because we are applying 0.7 volts between base emitter. So when voltage between base emitter is 0.7 volt, at that time the intersection occurs when emitter current is 9 milliampere. ठीक है?
Yes, sir.